Okay, example 2 for curve sketching. Here we've got a rational function. So if I'm going to try to follow along the curve sketching algorithm, but I'm going to make a little changes here and there because there's things that I like to combine or to do in a different order to make things a little bit more efficient for myself. So again, that curve sketching algorithm is just a guideline that is there to keep track to make sure you don't forget about something for your curves. Okay, so for this one, let's look at the domain. This looks like it has a restriction. If we factored this, we'd be restricted at 1 and -1, so we'll have to keep that in mind. And then x-intercepts, wherever the numerator could be a 0, which is at 0, and then y-intercepts, what happens when we plug in x being 0, we would also get a 0, so this thing's going through the origin. Okay, next thing on the algorithm is to look at asymptotes. So I'm going to look at my horizontal asymptote. Let's just put this whole thing up and then talk about it. So the highest degree term in our function that's here is x squared, so I'm multiplying everything by 1 over x squared, numerator and denominator. When I distribute that in, then I'm going to get a bunch of these reciprocal terms. As x approaches infinity, these are going to go to 0, so I'm going to get my horizontal asymptote at y equals 0. If I create the function f of x minus L, then this is the same function minus 0, which is just itself, so this is basically just f of x, and I'm going to chart this out based on where I am going to have restrictions and where I'm going to have zeros. So any place where signs may change. And then I've put in all my factors and I've populated this thing so that what I'm really just paying attention to for the horizontal asymptote is this, because this is saying towards negative infinity. I'm below the asymptote, and the asymptote's at 0, so I'm approaching it from below. And then this side, towards positive infinity, I'm above the asymptote, and my asymptote again is at 0, so I'm a little bit above it. Okay, we'll come back to this chart and talk about how we can use it for vertical asymptotes in a second, but let's do the vertical asymptotes separately. So here we had restrictions at 1 and -1. So let's see what's going on. Okay. At 1, if I approach it from numbers a little bit greater than 1, then I have factored this. I'm going to be taking that limit as x approaches 1 from numbers greater than 1. This is going to be a positive number, it'll be a 1. This is going to be a positive number, it'll be a 2. And then this will be something close to 0, but it's a little bit more than 0. And then here, since I'm dividing by 0, I'm going to be approaching infinity, and since I have no negatives, it's a positive infinity. On the other side of 1, when I approach 1 from below, same kind of idea. This is still positive. This one is still positive. This one, though, is going to go to 0. But now when it goes to 0, it's going to be a little bit of a negative number. So I'm dividing by 0, so it's an infinity. But I've got a negative number, an odd number of negative factors that's there. So it's going to negative infinity. And then same kind of idea is going to happen over here when I approach -1. If I plug in -1 here, this is a negative. If I plug in -1 here, it's negative. If I plug in -1 here, that will now go to 0, but it'll be a slightly positive number because it's a little bit more than -1. I've got an even number of negatives, so it's a positive number, and I'm dividing by 0, so it's infinity. And then same kind of logic's happening down here. So I have all my behaviors around my vertical asymptotes, and not only that, but because I did it in terms of these limits, I've actually shown that they're vertical asymptotes, because that was kind of the criteria required to find vertical asymptotes. We needed for the limit on either of the sides to be going to either positive or negative infinity. And then our behaviors that we found here, they should kind of correspond as well up here, that if you look on either side of -1, on the left side of -1, this is going to go down the asymptote. This one's going to go up the asymptote because of the negative and the positive that's there, which is kind of what's going on here. That's the left side, it's going down. Right side, it's going up. And then here on the +1 asymptote, on the left side, it's going down. On the right side, it's going up, which is also what we found over here. So this chart kind of summarizes everything for us in terms of asymptotes. Okay, then let's move on into critical numbers and such. So here, let's take the derivative. So if I want to take the derivative, I'm taking the derivative of this, so I'm going to be using a quotient rule. Okay, so if I take my quotient rule, I should get something that kind of looks like this. That is my derivative of my numerator times the denominator, then subtract numerator times derivative of denominator over denominator squared. And then simplify this to see if anything could possibly factor and cancel. I can common factor the negative, but this is not going to cancel. And if you noticed here, this was the difference of squares, the x minus 1 times x plus 1, and because it's squared, that means that both of those are just showing up, so I just rewrote it like that. Now this is not a difference of squares, it's a sum of squares, which means that I can't factor it. So this thing here produces imaginary numbers. There are no zeros coming out of this. So if I'm looking for critical numbers, then I can't get any zeros from my numerator, but I can get some values that are restricted in my denominator. Those I'd have to consider, but I already know that they're vertical asymptotes because I just proved them, which means that in this case I have no critical numbers. So because I have no critical numbers, that means that this thing that I'm going to be drawing, this function, is not going to have any local extrema. Okay, now I haven't charted this because I'm going to wait on the chart. I like to do it all at once so I can summarize stuff. So what I'm going to do next is, out of order of the curve sketching algorithm, I'm going to do step 6 next, if you're actually following along with the step numbers from the curve sketching algorithm, by taking the second derivative. Now this one is a very complicated derivative in terms of the polynomials and rationals that we've seen before. Now one tip that I had mentioned in class earlier is that all of these from my first derivative, these are all versions of the first derivative. What I can choose when I take the second derivative is any of these to use to take the derivative. I don't have to choose this very last one. In fact, this last one's not even a good choice because the denominator is more complicated in terms of taking a derivative. So what I'm going to do is actually take this one here, because this is a little bit simpler. I've got a numerator that's polynomial, and I've got a denominator that has a much simpler, I guess, chain rule associated with it than here. I'd have to do a product and a chain rule. So I'm going to take the derivative here, and I can again choose any of its versions. So I'm going to take the derivative here, which again is going to require a overall quotient rule. So I'm setting this thing up with a quotient rule. So here's my derivative of the numerator times denominator. Then I'm subtracting the numerator times the derivative of the denominator, which is now requiring a chain rule. So the 2 came down, there's a 1 up there, everything inside stayed the same, and then take the derivative inside. And the whole thing is being then divided by denominator squared. So that's what our quotient rule says. And then what our task is then going to be is to clean this thing up so that we could find some possible points of inflection. So I'm common factoring out as much as I can. So I took out a negative 2x. I took out an x squared minus 1 that was appearing in both. And then this is kind of the lump of terms that are left over I'm going to need to clean up. And when I simplify all this stuff, then I'm going to get something that kind of looks like this. And notice that the denominator had lost a degree because I used an exponent rule here. I've got x squared minus 1, another x squared minus 1. So powers with a common base, keep the base, subtract the exponents. So that's what I've done here. And then inside here I can take out a negative as a common factor, and it'll cancel with that negative. So here is my cleaned up, simplified version of my second derivative, which means if I'm looking for possible points of inflection, I will have one at 0. I could have one, this doesn't have any zeros, so nothing there. Or I could have it at any of the undefined values that I would get here, but I already know those are asymptotes, which means I only have one possible point of inflection that I'm going to need to consider. But I've got those asymptotes that are still going to be part of the overall graph. Okay, so I've got all this information. What I'm now going to do is kind of compile it in my chart before I sketch it. So what I have to keep in mind, and I'll kind of flip back and forth between these. Let's keep that up here. Here I'm going to chart out my very first derivative. And how I've charted this is I've put in the asymptotes, because they are restrictions in my domain. And I've also put in that possible point of inflection. So any critical numbers would also be on this list. Any other possible points of inflection would be on this list. Any restricted values would be on this list, breaking up my domain. What I've put in then here, these are my factors in my first derivative because I'm going to be looking for a summary of my first derivative, and then I've populated my table like we did previously. So if I summarize this, then I know that I've got a negative. This was an asymptote that I had to be aware of. Some negatives, another asymptote, and a negative, which means this function, everywhere where it is defined, it is decreasing. It's not decreasing everywhere because there are places where it is not defined, but wherever it is defined, it is decreasing. Okay. In terms of the second derivative, I'm going to be now putting in all of these factors. Oh wait, I made it a little bit better. So I'll put in these factors, and I will summarize my second derivative. So I've got my 2x, my x squared plus 3, and then each one of those, the x minus 1 and the x plus 1, that are getting cubed. Okay, when I put that stuff in, I am kind of summarizing it below, which means from the second derivative, I know concave down, vertical asymptote, concave up, then concave down, which means here, that's a point of inflection, vertical asymptote, concave up again. Okay. And like how I showed you guys before the break, if I take these two ideas of what my first derivative and my second derivative tell me, they're telling me decreasing, concave down, then I can just have a quick little sketch of what that would look like on the original function f. So I've summarized each one of these. So decreasing, concave up, decreasing, concave down, decreasing, concave up, asymptotes, point of inflection. So I need to put all of this stuff into my graph, as well as anything that I had said previously. And I said that we had intercepts that were going through the origin, so that's going to go in. And I've got my behavior of my asymptotes that's also going to go in. Okay, so here's my graph then. And we'll talk about it, putting it together. So this is how I would do it. First thing I would put in, I would kind of go through it in order. I had intercepts, so I would put in that point first. Then I'd go through and look for asymptotes. I have a horizontal asymptote at y equals 0. I have vertical asymptotes at -1 and +1, so those are all going in. Okay. Then from my chart, I would put in any new key points. I've got a point of inflection that's there. And then I can start putting in the rest of the information. So from my asymptotes, I knew the end behaviors. So I know this is going to be above, this one's going to be below. And I knew the behaviors on either side of the vertical asymptote. And then I can now start putting in these shapes. And then this is what my function is going to look like.